this will go right if we do it this way, okay?
Okay.
You see, you said you wanted us to do Euclidean today, right?
Yeah, let's do Euclidean
Well,
geometry.
then I have a problem with that.
Why?
Because tomorrow of all days,
Mhm.
there's a school event function that's going to need us to present probability.
Probability.
Yes.
So you'd like to do probability?
I would like us to do probability and this time get in probability.
Okay, that's fine. You said you're not able to attend Saturdays, right?
Oh no, if we do this
Uh-huh.
and I ace it tomorrow, I'll be able to attend.
Okay,
They'll give me a free day.
They'll give you a free day.
Yes.
Okay. So we only have 1 hour because we spent the whole hour talking about philosophy. So that's
why do we act like philosophers?
so
You are out there talking like Rene Descartes. And I'm over here thinking I'm Pythagoras.
no.
You're like, my good sir, let's do this. Oh, my good sir, let's do that.
No, so my approach is I would like to ask and find out from you, my learner, what it is you'd like to study for the day. And then we focus on that. So if it's probability today, let's do it. But I believe we do have a class on probability on YouTube, or do we not?
We do.
Wait, let me just check. Let's just check. Probability.
Get ghost.
Because if not, we will continue with Euclidean, and you will learn probability from this stuff that we've already looked at.
The thing that I want to jump in on probability
is what?
Is intersection.
Intersection of different sets.
Yes, I want to get that grasp of intersection. Like, there's a probability whereby they can give you a problem. There's an intersection, right? And then there are a couple of values missing. They'll ask you to find those values. I want to know from you, Mr. P, being the wisest person I know currently. Keyword currently. So, to learn from you a fast method of how to get to those problems.
Okay, we did do probability. We just didn't record it. That's the unfortunate part. Okay, so let's do it again, and then this time we'll have it on record. Okay, it's fine. We'll continue. So, open with Chrome so that I can search for the different pages. That's fine.
Yours doesn't control G.
For some reason my Acrobat reader is got issues. And I've had to
Unit 8 probability.
145. So let's make that 170. Oh, so it's opened up in calculus. There we go. So we'll start this again. Okay, but yeah, okay, cool. So we'll start with probability. This jam here next to the camera.
This one?
Yeah, that one there. Okay. Probability. Thanks. Alright, and today is 19th August 2024. Alright, so probability is how likely something will happen, right? How likely an event is to happen. For example, when you're watching the weather report or the weather forecast, and you'll get something like, okay, in our region, let's say this is Mzansi. Yeah, such a bad looking Mzansi. Coast must look something like that. Swaziland, Limpopo, Northwest, Northern Cape.
Limpopo, not Limpopo.
No. Alright. And then they say there's a probability of rainfall there, and there's a probability of a heat wave there. That one? And then, yeah. And then there's likelihood that it would rain. Those are raindrops, let's just assume. And they put like a 80% there, right? So this would be the probability of rainfall, ne? Is 80%. That we get, ne? All right. So you can do the next slide. You can also take it to things like, what's the likelihood that if I batch up my numbers and all the 6 numbers are each of the 6 people in my household's birthdays? What's the likelihood that those numbers will show up in the correct order or whatever order, but show up in the winning lottery numbers, right? And then the scale of probability, there's 0, which is impossible. There's no chance it will happen. For example, we do have the chance that the moon will cycle around the earth and sometimes become in a position where it is between the sun and the earth, and then you have a solar eclipse. And you do have the event where the earth, as it's rotating around the sun and the moon rotates around the earth, that the earth would be between the sun and the moon, and then we get a lunar eclipse.
A lunar eclipse?
Yeah, when the moon ought to be visible, but the earth's shadow is cast onto the moon at night, and then the moon is in an eclipse.
So is it like day?
No, it happens at night. You'll see it at night. But instead of the moon being visible, because the earth is between the sun, which the light from the sun is reflected by the moon, would be blocked out by the earth's presence in between the two. The earth's shadow casts onto the moon, and then it eclipses the moon. So then you have a lunar eclipse.
I see.
But you will never have a situation where the earth is on the other side, the sun is in the middle, and then the moon is on the other side.
That's a probability of like what? 0?
0. So that's these kinds of events, right?
Okay.
So that you call that an apocalypse. So it's not gonna happen. By the way, apocalypse means revelation.
Oh yeah.
Not yeah. So it means something that is a veil getting lifted. Then you have 25%, which is poor chance, unlikely, but possible. So it's possible, but slim chance of it happening. Then you get 50%. So this is like a coin toss, right? So fair chance, e.g. coin toss. And then you get 75%, which would be good chance, quite likely. Quite likely. And lastly, you have 100%, meaning, oh yeah, it's definitely gonna happen. So I'm definitely gonna write definitely gonna happen.
Wow.
Going to happen. Alright?
Definitely gonna
Happen. Okay, so that's the scale. Alright? We can work out the probability using a formula. Next slide, thanks. And that formula is probability equals number of favorable outcomes favorable outcomes divided by the number of possible outcomes. All right, so it's very important that we pay attention to these words favorable and possible. All right?
Mm-hmm.
Because favorable is what we desire. And possible is what could happen. And those are two completely different things.
Mm-hmm.
So, right? So there's a I think it's Murphy's Law. I'm not sure if it's Murphy's Law, but in the movie Interstellar they explain it as whatever can happen will happen.
Whatever can happen
Will happen.
That's Murphy's Law.
Murphy's Law.
Yes,
Okay,
it is
cool.
Murphy's Law.
And that's different from, oh, I want this to happen. Because, I mean, the strawberry does not ripen according to the monkey's appetite. Alright, I don't know how you say Gaspedi, if you know that saying, but the important thing about that saying is it also speaks to probability. Right? Yeah, the strawberry does not ripen according to the monkey's desire or appetite. Yeah, so this ratio can be expressed as a common fraction e.g. 1/2 in a coin toss. It can be expressed as a decimal.
Okay, we said favorable outcome over possible outcome, meaning that the possible outcome in a coin toss is heads or tails.
That's a possible outcome.
Yes, they're true.
They're true.
I believe the favorable outcome is I want heads
and I want tails.
So it's going to be 1/2.
Yes. So we each have the possibility of getting one.
I see.
All right. And the probability is always between 1 and 2. 0 and 1. Yes, not 1 and 2.
1 and 2, I was like, what?
Always between 0 and 1. That's very important because 0 would be 0% chance and this would be 100% chance. Alright.
Mm-hmm.
Now we're gonna look at now we're gonna do a little exercise on the internet, right?
Mm-hmm.
We'll use a coin toss. So we're gonna look at theoretical and relative probability. Relative probability. Okay? So again, looking at the coin toss, possible outcomes are heads and tails, right? So heads and tails are possible outcomes. All right. And this means 50% chance of either happening. All right. And this means thanks. This means there is a theoretical probability. of 1 over 2 for either outcome, ne? All right. So the theoretical probability of heads is the probability of H. So the probability symbolized as that of heads, which would be the outcome for heads, right? Theoretical probability for heads, which means then P of T would be
Theoretical probability
for tails, right? And this ought to be half as well as that one. Possible outcomes are 2, desired outcomes is 1, right? Now, this in contrast to relative probability, which we can illustrate with an experiment. Ne? And the relativity depends on how frequent we do this experiment.
Oh.
Yeah. The relativity comes from how frequent we do this experiment. So let's quickly open up coin toss generator. Okay. So we'll have a coin flip simulator. Random coin flip generator. Nah, this one doesn't look nah. Something that will make a sound like cling.
Wow. You like that cling?
Yes. So
I'll
which one?
Heads.
You'll take heads.
Give me heads
So
so I can build up knowledge.
Siama will take heads.
I'll be counting.
And we're gonna do this 10 times. And Mr. P is tails. It's just weird. Like, I thought you'd take tails because it starts with T.
Not really.
Alright, so.
I prefer heads because that way I can build up knowledge.
Get
it? Because
yeah,
the
heads.
brain
Alright, so we're gonna start 1 and then go 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll just stop at 10 in the interest of time. All right, so let's just so we'll have that. All right, so the first time we so whenever it lands on heads, I'll put a tick in heads for your notch. And whenever it lands at tails, I'll put a tick in tails for my notch, right? Yeah, so we're gonna flip it. That's the first flip. And it lands on tails, so I get a notch. Then the second one, and this time it lands on heads, so you get a notch. Third time it lands on heads, well done to you. Fourth time it lands on tails, so that comes to me. Fifth coin toss goes to tails. Sixth coin toss goes to tails. Okay. Seventh coin toss goes to heads. Well done to you. Eighth coin toss goes to heads again. All right. Ninth coin toss goes to tails again. Well done. And the last coin toss goes to tails. All right. So relatively speaking, even though between heads and tails, we each have a 50% chance, but relative to the 10 times, what does that mean? It means that for Tiamo, T of heads would be 1, 2, 3, 4 out of 10. And, or rather, let me say the probability of heads for Tiamo and the probability of tails for
Mr. P
yes, for Mr. P is 6 out of 10. Yeah, 6 out of 10. But if we do this 100 times, we don't know what the outcome would be. But let's look at the example that's given. Jake flips a coin 100 times and records his results, and he flipped heads 55 times. So that means the relative frequency of heads is 55 out of 100. And that could change because in another day, it could be something else.
Yeah, that's true.
Then the relative frequency of tails would be 45. So it would be the difference between 100 and 55. That would be the relative frequency of tails. So it means tails showed up 45 times out of 100, whereas heads showed up 55 times out of 100. Now, if he does the same experiment 1,000 times, it is likely that heads and tails would come up almost about the same number of times. So he's likely to get 499 to 501 times. Now, this relative frequency equals or is close to the theoretical probability of 2. So what does that tell us? We do this test a whole lot of times. It then proves the fact that the probability of heads versus the probability of tails is 50%. Because if it goes 10,000 times and it gets us closer to 4,999 or 5,001, then it means that's almost like 50-50. And the more times you do it, the closer and closer and closer it will get to 50% on the dot.
Is it possible for one of them to overlap in this type of situation?
Overlap how?
One of them gets 499, the other one gets 599.
Ooh. But now the math does not math there.
That's why I said overlap.
Yeah.
Overlapping doesn't make sense. It just happens.
Yeah. So, but the point of the experiment and this discussion is to say, if we do the coin flip 10,000, 100,000, or even 1,000,000 times, the odds that we would get heads or the odds that we would get tails would be almost the same.
Close to 50%.
Close to 50%. And the more times you do it, the closer and closer and closer and closer it gets to 50%. So then it validates the theoretical probability.
I see.
Yeah, so that's relative to how many times we're doing this. So it's called relative frequency, right? Yeah, so in each experiment, that's a relative frequency.
I see.
Yeah.
This event of dice.
Okay, so let's just look at a couple of key points to note.
This one of dice tends to be a lot, appears a lot. I understand the question.
Yeah.
So I came prepared.
You came prepared, okay. All right, because we also could have done it. Yeah.
They said that, remember, one die,
2 dice.
2 dice. So an event is happening or an activity that comes on result. For example, rolling an even number is an event with given outcomes. An even number is like
2, 4, 6.
Yeah. And an outcome is the possibility.
Is the possible result of an event.
Example, the possible outcomes of rolling a die are
1, 2, 3, 4, 5, 6.
So if they say, what is the probability of rolling an even number on both dice, how am I going to write that in a form of...
That's a very good question. We're going to get to that. And I think knowing this knowledge or knowing this kind of stuff would probably make you a better Ludo player.
Ludo player.
Because Kawana Tlelema dice are Ludo. They always play with such small dice.
I mean, they like them. Kumane basubile kuwa. What's happening? Awachaya.
Yeah. I kill the chow. Nice show. Yeah, I'm going to brag. I'm going to brag. Yeah, so.
You got a million views.
It is what it is. You gotta say braga enough times. The relative frequency of that being said in your video will probably result in more viewers. So let's look at Venn diagrams. Venn diagrams. Who is Venn, by the way? Because it's likely that this was named after someone called Venn. So let's look at Venn. Where does that come from?
It's another Pythagoras and the Cartesian plane.
Definitely. So, what is a Venn diagram? It is an illustration that uses overlapping circles to show the logical relationship between two or more sets of items. So circles that overlap have a commonality, while circles that do not overlap do not share any of the other circle's traits. And the Venn diagram was popularized by John Venn in the 1880s. So literally over 140 years ago.
John Venn.
Yeah.
Created the Venn diagram.
Alright, so how they work, they're useful for illustrating how different concepts or factors intersect with one another. They can show at a glance how things are similar or different, or how and where they overlap. Oh, by the way, there's a thing if you want to find the sweet spot of what you want to do with your life. It's called ikigai. So I think this is a
what's ikigai?
Ikigai. It's a Japanese philosophy for finding meaning in life and purpose in life, right?
Mm-hmm.
So I think you should take note. And let's look at ikigai, right?
Mm-hmm.
It's so that you can find the sweet spot, which is called the ikigai, right?
Mm-hmm.
So there's what you love. Then there is what you're good at. Then there is what you can be paid for. And then there is what the world needs. Ish. Yeah, no, I tried. I'm supposed to have.
Those 4 rings don't look like a Olympic. Now to me,
Nah, mine don't
make it to the Olympics.
Mine are not.
Nah.
Even Audi rejects that. Wow. Wow. So it's supposed to be. Okay, let me try a different strategy. So I'll do them using a cross. And then, so halfway between those two.
My brother, they reject that.
And then.
I have an idea of how you can do it.
Oh, but no, pass. And here's how, right?
Mm-hmm.
So you get those 1, 2, 3. It's just these ones are bigger. 4, which are these things. Ding, 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 ding.
Do you know what they call that type of thing in
What?
South Africa when you go?
What? Oh, but okay, let's work with this sport, guys. But it's what you love, right? What you're good at, what you can be paid for, and what the world needs.
All of those references, especially the smiley one, that one has been.
And what the world needs, right?
Mm-hmm.
So this one here would be, so between what you love and what you're good at is your passion. Between what you're good at and what you can be paid for is your profession. And between what you can be paid for and what the world needs is a vocation.
What is a vocation, by the way?
Have you watched How to Lose Friends and Alienate People?
No.
They keep telling this guy, this is not a vacation, it's a vocation. So think about an internship. Think about not even an internship. Let's say you are. Okay, let's just look at the definition. Vocation. I think that would make it easy. Vocation. Alright. Yeah, in occupation or employment. So the difference between vocation and profession would be, let's say you study towards being a doctor, right? So then you become good at it. And because you're good at it, you get paid for it.
Now, that's what a vocation or profession.
Yeah, the one of Ikigai is a bit, it's a bit tricky. But anyway, and then you also have mission, right? There's another one which just has three circles overlapping. I believe it's what you love, what you're good at, and what the world needs. And if you can find all three of those, you'll fall here.
Lord have mercy.
You'll fall here, and you'll live one of the most amazing lives for yourself in this lifetime. All right? But the whole point is you can also take Venn diagrams into your personal life.
Yes, that one I've heard from my mom before.
Oh, that's fantastic. I love that for you, that you got it from your mom. So now it creates an emotion within your heart, and hopefully then this topic of Venn diagrams does stick, because that's also another great way to learn when we have an emotional attachment to that which we absorb.
Yeah.
Right?
I call those hyperlinks.
That's an interesting way to think about it. I like that. So our rectangle represents a sample space, right? So we'll just put S there for sample space.
Yeah, well,
S.
We are there. Let's see now.
We're out there.
No, we're there. We wanted us to be.
Yes. And then we have two events in our sample space. There's event A. So we'll call this event A. And then we have another event. Let me make it blue. And we'll call this event B. Alright? And then in the middle is event A and B. Alright. So that's just at a high level how we can think about Venn diagrams in the context of a sample space, right? So in the context of Ikigai, that would be the sample space would be everything and everything within anything and everything within your reach, within your skin, within your reach, and outside of your skin in the world. That would be the sample space, right? And then maybe event A would be the things you love. event B would be the things you are good at. Event C would be the things you can make money from. And event D would be things that the world needs. That's why I was very specific about things inside of you, your skin, things outside of your skin, and the whole nine. Yeah, man. So, and maybe I can get corrected on my use on this, whoever's watching. But yeah, it's just a way to tie this to everyday life. So, as an example, so in our example, we have a sample space, ne? And that sample has got the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Yo, and then what just happened? To Jamboard, like it just got reloaded. It just literally jammed on me, on us. I guess that's why it's called Jamboard. Hey, Google.
Literally just jammed. I was like, that's why it's called Jamboard.
Hey, Google, what are you telling us?
Jamboard puts the gem. It puts the gem in Jamboard.
It puts the gem in Jamboard. And you're not the first letter to make fun of it. Oh, my word. Oh, my word. Waiting beat. Waiting. Yo. No, I need to reset Jamboard again. So I haven't restarted it. Waiting the soup. Yeah.
Support of higher power must be paid where he has the time to sit back.
Are you still laughing at my pew comment?
The way you did it, you were on point. That's him.
We'll talk about that. I don't want to capture that. I don't want to capture that commentary on video. This is for my class.
He'll be here with his theme song playing. The guy will leave South Romania. Come to South Africa.
This thing didn't even capture up to 10 and I've already gotten to 10. 3,
What's happening?
it didn't capture 3, 4, 5 up to 10, but I'd already gotten there. But anyway, 5, 6, 7, 8, 9, and 10. But again, as in life, sometimes you get setbacks and you have to start from where you know, where you had already passed.
Wow.
But yeah.
Hey, you pass it again, you get stronger.
Yes. So in this exercise, we must draw a Venn diagram, ne? Venn diagram. All right. So we have event A, and it's a set of prime numbers. Now, what is a prime number? Remember, it is numbers greater than 1 that can be divided by themselves or 1. They can be divided by...
or 1.
Yeah, it can be divided by itself or you can divide it by 1.
So when I divide it by 1, the answer must be 1.
No, the answer must be itself.
Oh.
The answer must be itself. But it's greater than 1. Alright? And these prime numbers, let's circle them in blue. So event A would be in blue. So numbers that can be divided by themselves would be 2, would be 3. 4 divides by itself but also by 2, so that doesn't count. 5 is a prime. 6 divides by itself but also by 3, so it doesn't count.
7.
Then there's 7. 7 divides by itself. Yes. What about the number 9?
You can divide 9.
It can divide by 3, so it doesn't count either.
Oh.
Yeah, 9 can be divided by 3, so it doesn't count.
And 10 can be divided
by 5 and by 2.
Ish.
So it doesn't count.
We only have 4.
So we only have 4 prime numbers.
Yeah.
So this set is 2, 3, 5, and 7. That's how you know someone is from Polokwane. It's chai. Ongo brag. Then event B is a set of even numbers.
Oh, we got 2.
Okay.
And we got 4.
So even numbers will make red. So we've got 2. Then we've got 4. We've got 6.
We got
8 and 10. So we've got 2, 3, 4, 5 of these. Okay. That's interesting. So event B will be B.
Oh, we got 5. Oh.
Yeah, we got 5 even numbers. Yes, we got 5 even numbers. A count of 5.
2.
So 2, 4, 6, 8, and 10.
2 is common.
So 2 is the overlap. Yes, 2 is common in both. You see, that's why it has the blue and the red circling it.
That's why I asked you
about overlap.
No, that's why I asked you. You said that we have 5, and I said 5 because I can see 2. It's coded in blue.
Oh.
And then I remembered. Oh, you said overlap.
Overlap.
Means
yes.
there's intersection.
Yes. So that goes back to the questions you had before the class started.
Yes.
Alright. So we'll get to answer all of those. Ne? So then what this means is if we are to draw a Venn diagram, our sample space would look something like this. So this would be S. And then event A would overlap event B. Right? And in event A, we would have 2, 3, 5, and 7. And in event B, we would have 2. So let's put the A there. And let's put the B there. So in event B, we would have 2, 4, 6, 8, and 10. And where does that leave 1 and 9?
In the sample space box.
In the sample space box, because they're also part of S. So 1 and 9 would be floating there in the sample space box.
They're just floating.
They're just floating. They're like
outer space.
Maybe they're like valence electrons. I really don't know.
But hey, as long as they're from planet Earth.
That one got you good, ne?
Mr. P, where do you come from? I'm from planet Earth. Let's leave it there.
I don't want to explain a lot of things, man. But anyway, so use the Venn diagram in the previous example to explain, or rather to determine, the probability of event A. Okay, so possible outcomes are made. How many? Let's start there.
Possible outcome.
Yes, so let's just start there. Remember, probability is number of favorable outcomes
over number of possible
outcomes, right? So possible, we have 10, right? So that means our denominator is always going to be 10. Right? All right. So favorable outcomes for event A is 1, 2, 3, 4 of those. right? So for probability of event A, the number of favorable outcomes
is divided by the number of possible outcomes, which will be 4/10.
Yes, so that would be 4 divided by 10, which is 2 divided by 5, which is 0.4, which is 40%.
Hey, check Ghost. Let's check you out. What do you wanna check? Yo, wrong mode set to the calculator. Tuesday.
Let me use my 4 divided by 10 times 100. It's 40. Yeah, 40%. Right? So in our sample space with the numbers 0 to 10, prime numbers occur 40% of the time. So 40% of the time, prime numbers occur 40% of the time. That's what that means. And then for even numbers, the number of favorable outcomes
divided by the number of possible outcomes,
mm-hmm.
which will be 5 divided by 10. Then from 5 divided by 10, well, it's
would
going
be
to be
5 divided by 10.
1 over 2,
which is
0.5,
0.5, which is 50% of the time. Therefore, even numbers, and this makes sense, between 1 and 10, half those numbers are even numbers.
Yeah. But I have a question for you, Mr. P. When they say therefore, why do we do those 3 dots? Is it important to do it? Can't I just do equal sign and leave it?
There's a whole lot of symbols that are used in maths, right? And depending on what you decide to study beyond matric, you'll come across them. And each one of them has got a specific reason why it's used. When I was in engineering class, we learned of using if and only if, which you write with 2 F's.
If
and only if.
Only.
And there's a specific context in which you use it. Another one that we learned was this sign, which means this implies. And it can also go back and forth. This implies and is implied by. And then there is because. So there are a whole lot of symbols that are used in maths, and they have specific contexts.
So this one with the 3 dots forming a sort of triangle
pointing up.
Yes, it means therefore.
Therefore, yeah.
This one of pointing down, it
means because.
Okay.
Yeah. So there's oh no, I don't want to clear the whole frame. I just want to clear these ones. So there's a lot of symbols. I don't know all of them. I would be, if I was a specialist in math, I would know a lot of them, definitely. But I'm not a math specialist, no. I'm just a guy who's able to impart concepts of and communicate them in a way that can be grasped. And also
guy with the computer.
Just the guy in the chair with the computer. Anyway, so but you get it.
Yeah, I get it.
So half the time in our sample space from 1 to 10, we get even numbers. And the same could be said for odd numbers. I mean, if that was an event that we have to work out the probability of, we'd probably come to that conclusion as well. Probably come to that conclusion as well.
Probably. It's a high probability.
Then there is the probability of A and B. A and B being the occurrence of the overlap. Right, so this is the overlap. Right? So the probability of, so let's look at the number, let's just look at it from definition, right? So A and B
Does A and B still contain the same rule as the probability of A alone? Like, does it say the number of favorable outcomes divided by the number of possible outcomes?
Yes, because we have to stick to that definition.
Okay.
Yeah, so let's stick to that definition. So the number of favorable outcomes divide by the number of possible what am I writing? Outcomes. Outcomes. It's like, okay, what happened there? So, where A and B happen at the same time, if we look at it from the Venn diagram, it's where you actually have the overlap between event A and event B. So the only time in our sample space where that favorable outcome of having event A happen at the same time as event B is only at the number 2. That being said, that favorable outcome happens once out of 10 times, and that is 0.1, and that is 10% of the time. Therefore, to have a number that is both a prime and even number happens 10% of the time. That's what that means.
Now I can see where the 10% of the probability of A went to. Because probability of B, that even numbers okay 50% of the time, and prime numbers only okay 40%, which is 90%. So where's the 10%? Now we found where's the 10%.
That could be a way to think about it. I wouldn't want to say 100% you're spot on. My brother would probably, because he's a statistician. So he would probably have something to say about that. But I'm going to ask him. I'll ask him.
Yeah,
I'd love to ask him.
Because there's no way for something to come into the world as an 80% or 90%. You come in as 100%.
And then something has to account for the remainder.
Yeah, yes. So like, if they say you're 50%, you gotta have a twin brother who's the other 50%. Then you get that 100%. But if one of you is 40%, then that means you must have a younger sibling who's carrying the 10%. All three of you create 100%.
I see where you're getting at. I see what you're getting at. I see what you're getting at. I see what you're getting at. Yeah, I see what you're getting at. But let me ask an expert, someone who works with these things professionally.
You're gonna be like, I una manga, it's not like that.
Or they might have something to say. But for now, let's just focus on this theory, right?
Yes.
Okay, so let's look at something else.
Such as?
The probability of A or B, right? And the probability of A or B would be, we're looking back at our sample set, ne? And the probability of A or B, number of favorable outcomes. So A or B would be noma yini, but it could be either A or it could be B, right?
Mm-hmm.
This doesn't include those freelancing numbers that don't really have where they belong, like 1 and 9.
Oh, yeah.
So that leaves us with 8 numbers.
Remind us.
If we look at 1 to 10
Mm-hmm.
and we remove the numbers 1 and 9, we're left with 8 numbers.
I concur.
And those 8 numbers give us event A or event B. They will give us either prime numbers or even numbers.
We're dealing with prime numbers and even numbers, right? Not odd.
Yes, not odd.
Okay.
We're dealing with prime numbers and even numbers.
Mm-hmm.
So the favorable outcome of event A, which is prime numbers, or the favorable outcome of event B, which is even numbers, is 8 numbers. So out of the 10 that we originally had, only 8 would give us prime or even numbers.
Yes.
So that's what we write there.
No.
So number of favorable outcomes over number of possible outcomes would equal 8, because 8 numbers give us either prime or even numbers. Only 8 out of the sample set. 1 and 9 are ditlhakane because they are neither prime nor even numbers. And possible outcomes is 10 because that's our baseline, that's our denominator. So that means that 0.8, which is 80% of the time. Therefore, to have numbers that are either prime or even happens 80% of the time in S, in our sample space.
I concur.
Alright. So to have a number that would either be a prime number or an even number happens 80% of the time in our sample space 1, 2, 3 up to 10.
Yes.
Alright. Then we have another conclusion. If we take the probability of event A, we add it to the probability of event B, and we subtract the probability of prime numbers and even numbers happening at the same time, so A and B, we will get how much? PA was 4 out of 10. P of B was 5 out of 10. And PA and B was 1 out of 10. And this gives us 4 plus 5 is 9 minus 1 is 8 out of 10. But this also equals the probability of A or
It says 4 out
B.
of 5. So I'm confused.
Yeah, 4 out of 5 is 8 out of 10.
Why did they do that? Why did they make it 4 out of 5? Because in primary I was taught that the denominators are the base numbers, right?
Okay, I get what you mean by base numbers, like the one you refer to as the factor.
Yes.
Yes. So if you're going to look for a common factor, you'd refer to the denominator.
Yes.
That's very good. But also, if you think about simplifying the fraction, making it in its simplest form where you cannot find a factor that goes into either denominator or numerator. if you think about the number 2, 8 can be divided by 2 to give you 4, and 10 can be divided by 10 to give you 5, hence 4 over 5. Yeah, so that's the simplest form of the fraction.
No other way of breaking it down again.
Yeah, you can't simplify it further. Right?
Yeah.
So this conclusion tells us that as a rule of thumb, the probability of event A plus the probability of event B minus the probability of event A and B equals probability of event A or B happening. So this becomes a conclusion that we can work with going forward, right? All right, so let's look at mutually exclusive events. Okay, you're still writing, eh?
Alright, you can turn over to the next slide.
Next slide. All right.
I'm just training my mind to like memorize most of the things that I'm doing.
Oh, okay, that's fine. But don't you get given these formulae in the exam or test?
Oh no.
Not the ones for probability.
Oh, those ones we don't get them.
Are you serious?
They say it's an exception or what they expect from you.
It's an expectation.
Yes. Actually, it is an exception because there are only a select few people who can be given that thing to see moments before we write. Only the exceptional ones, actually. So.
Really? Oh, I didn't know that. I thought you either all get the formula or you all don't get it. And when you don't get it, it means you memorize it. But alright.
Those who get it are like, how can I do this? The ones who are in dire need of it.
So it is an exceptional case. Okay.
It is an exceptional case.
Is it like special needs?
Yeah, special needs. But like, there are some of us in class, they can be like, 1 plus 1. Let me take out my calculator. You see those ones? Those ones are the ones we can show the formula like 1 plus 1 equals 2. Don't forget that. Okay, then they leave.
I didn't know that you can have school like that. That sounds very nice.
They're just trying to like balance the equation of learners because there's been an issue in my class whereby this girl feels like she's overshined by the class.
Is it?
Yes, because most of the cases she feels like she can hear the class's thoughts of her being a helmet. That's what my classroom call you when you have a good appearance, but your appearance don't match your mental capabilities. They call you a helmet. So she felt like the class was seeing her as a helmet when she's not a helmet. You see, a helmet, it protects outside, but inside it's hollow. So that's how they saw it. Well, that's how she felt. Ever since she told the teacher's been trying to balance this problem in class.
Are there other learners like that?
No, it's only her, specifically her. And like, at first I thought like maybe the other learners are just being rude to her, but then I saw it firsthand that it's actually true.
Okay, we'll talk about that after class. But let's just quickly go over this topic of mutually exclusive events because then it ties back to the question of rolling dice that you had initially.
Yes.
Alright.
If you roll a die.
So, mutual exclusivity, right? It means when events are mutually exclusive, it means they cannot happen at the same time. So that's where the
mutually
exclusive.
Exclusive.
Check the other die out. Where's the other die?
I heard it say roll a die.
Oh, okay.
And die is 1.
1 die. 2 dies.
See, we learn from Mr. P.
I'm also learning again. Relearning. So, mutually exclusive events equal events that cannot happen at the same time.
Mutually exclusive events or what?
So in other words, the probability of those events happening at the same time is 0.
Oh.
Back to the scale we started with, 0, 25, 50, 75, 100. Yeah. All right?
Mm-hmm.
And that's because exclusive comes from the word to exclude, which is to keep out,
Mm-hmm.
or not allow something or someone in. And mutual meaning applying to 2 or more people or events. Right?
Mm-hmm.
All right. So if we roll a die,
This die.
and we've got a die in front of us, that's great. So not to die as in to lose your life, but die as in die is singular for dice.
Isn't it singularity? Or is it singularity?
Singular form. Singular form. Singular, plural. Yes. Singularity is something else which not nanos per se, but like
I heard it from my English teacher today that she said what? She said it was an example she gave us.
Mm-hmm.
She said that gravity has a singularity point.
Yeah, I was about to say something sophisticated in physics, like yay, like there is advanced levels of physics and science where they speak about singularity, and it's but we'll learn about those in some other context. But for now, let's just stick to rolling a die, because at least it will make us play Ludo nice. That's
we want
more
to learn how to advance in
Ludo. That's closer to us here, Shiro. Chayamat dice. Chayamat. So if you roll a die, it's impossible for it to land on 1 and 6 at the same time. So
true.
So in other words, we have our die there. So if we have 1, 2, 3, 4, 5, 6, 1 is at the other side.
Beneath it.
Can
you change the colors though? I mean, it would. Trust me. The spots have different colors.
Okay, so let's say the black ones would be the 6.
Mm-hmm.
Okay.
The yellow one would be 1.
The yellow one would be 1. It's probably at the bottom.
It is at the bottom.
Of 6, no?
Here's 6, here's 1 at the bottom.
And then where's 2?
2, my dear sir. Here's 2. And counter to 2 is 5.
Counter to 2 is 5. So
yes.
Let's put 2 as blue.
2.
And 5 would be on the opposite end. So let's make it red. 1, 2, 3, 4, and 5.
Yes.
And then that means
4 and 3 are left.
So 1, 2, 3, 4, 5, 6. Okay, so 1, 2, and 3 would be green. Then the other side would be 4. So since we 1, 2, 3, 4, we'll make it white. I'll just make it hollow circles. 1, 2, 3, 4 to show that they're white. Okay. It's a bit complicated, but the point is probability of 1 cannot happen the same time. The probability of 1 and the probability of 6 are unique events, but they're mutually exclusive. Exclusive and cannot happen at the same time. Okay. So when we roll a die, what are the chances of getting a 1 or a 6?
The chances of getting a 1 over 6?
Yes.
1 over 6.
Let's calculate that. 1 or a 6. Ne? So P1 or 6. Remember, we have to use that formula. P A plus P of B minus P of A and B equals P of A or B. So that's where that conclusion comes in to place now. Comes into play. Alright, so it should be P of 1 plus P of 6
P of 1 and P equals 2. P
minus P of 1 and 6. So because this cannot happen, this does not happen, this does not feature in the equation. So we can just scratch it out and just have the probability of 1.
Something's happening.
What, are you okay?
I think I'm getting shoulder cramps. Yeah, it's been a while since I've done some exercise.
Is it, when last did you work out?
3 weeks back.
It was actually shorter than I have. Yeah, I have
3 weeks. I mean, it was a good workout, but then still 3 weeks.
Alright, we'll talk about that later. So yeah, the probability of 1 or 6 happening is a third. So 33.333 times of the time you roll a die, just over 30%. So a third of the time. So this means a third so a third of the time no, not a third of the time. Maybe my English might not be correct and it might be misleading. Yeah, because it was correct to use it in this slide when we were doing the sample set 1 to 10, because that was specific to the thing. But in this case, I cannot use the word a third of the time, but out of 100%, so out of 100%, 33.3% of chances could be 1 or 6. I think that's a better way to phrase it.
Let me read it and rephrase it.
A third of the chances we get to roll a die. Remember when we're tossing a coin, half of the chances we get could be heads or could be tails. So it's a fair chance.
Yes, it's...
So with rolling a dice, because it's also chance, a third of the chance could be a 1 or could be a 6.
Oh, because a die has 6 phases, and since it's only 1.
Remember, each number from 1 to 6 on a die has 1 over 6. What's 1 over 6?
The probability of 1 over 6.
1 divided by 6 is 0.1, so 16.7% chance, right? So you have 16.7% chance of getting a 1, a 2, a 3, or 4, or 5, or 6. Anytime you roll the dice, the die. Anytime you roll the die, you have a 16.6% chance of getting any one of the numbers from 1 to 6 for each of them.
16.7%.
16.7%. Because the probability of rolling a 6 on a die is it's 1/6.
The probability of rolling a 1 or... Did we do the or part?
Yes, we did it.
When we scratch out the part of n because that's an impossible event.
Yes, so that just means this scenario is for the probability of rolling a 1 or a 6. And you could apply the same to rolling a 2 or a 4, rolling a 3 or a 5. Angusha. But if we're looking at just one of these, which is just the probability of rolling a 1, just any one of these on the face, the probability of rolling a 2, there are 6 faces on a die. So the probability of having a 2 as your outcome. Favorable outcome is 1. Possible outcomes are 6. So it's 1/6.
Yes. That much I know.
Yeah. So for any one of the faces, favorable outcomes is 1, but possible outcomes is 6. Hence, each face has got a 16.7% chance of showing up, which is 1/6. Ne? But if we're going to look at the probability of 1/2, then that number changes.
It becomes what?
It becomes the probability of one face plus the probability of the other face minus the probability of both faces occurring. And since that cannot happen, we remove that. It falls off of the equation, which is what this expression is about here.
I see.
Again, so we could have, so we would like to have 1 and 6, but that's impossible. So why is it even in the equation? So that means we're only left with the probability of one of the faces.
Next time I won't stress myself about it.
Yeah, so it's also about being logical with what's happening. Because probability is a very realistic
type of topic
to touch, yes. I want not to say the others are not very realistic, they just start off very abstract. Yes, they start off very abstract, but probability brings it back to matter, brings it back to
see if you have common sense.
Common sense as well. Yeah, I like that. But common sense is not common to everyone, by the way. That's why.
I mean.
That's why people have very many disagreements. It's not common to everyone. Alright?
What is common sense to you?
And I don't like using common sense because I know it's not common to everyone.
Define it in one word.
I would say it's just being rational, being reasonable, being logical. And not everyone's going to be rational, reasonable, logical. So some people would reason from other perspectives and maybe the logic might not add up. It's like, why is the math not mathy? Why is 1 going to 3 before it goes to 2?
It's easy to say that when you're the one who's making the rules.
Also, that's the other thing. There could be bias. So that's why I don't like the word
common
or using common sense, because I could be speaking of a perspective of my experience, which could be less than someone else's.
Yeah.
And only to find that I'm not even aware of my bias, which comes from my limitation of awareness. Yeah, so so common sense is not common to everyone, no? Yeah. So, yeah. Possible outcomes for rolling a die. Roll a 1, roll a 5, roll a 6 on a Venn diagram. If we have a sample space. So that's our sample space. And this is possible outcomes for rolling a die. Alright, so to roll a 5, to roll a 1, to roll a 6, to roll a 4, to roll a 2, and to roll a 3. If you're just looking at 1 and 6, there's no overlap between all of these. Can you see that? They're all in the same sample space. All in the same sample space. But you cannot have overlap because you would not have one overlapping 4 or 3 or any of the other.
Due to the fact that it's a die.
The fact that it's a die, its geometry does not allow that to happen.
It cannot unfold.
It cannot unfold and then to the force the unless it's in dream space where dreams they tend to just not have
Logic. You just do whatever you want.
The way they happen.
Fishes fly.
And then as soon as it lands, when it stops flying, it turns into a lion. And then it moves a couple of steps, it's now a dragon.
It moves a mountain without touching it.
And then jiggy, you're in a car and you're driving it.
Dreams.
And then you're in Brazil. And then you're at the carnival, but then it's Oktoberfest in Germany.
The things we humans do with our minds.
So, yeah. So what this means is that when events are mutually exclusive, are mutually exclusive, then the probability of A and B happening equals 0. And this is important because it goes back to what we shared over here in this slide previously, right? Which is that, but now, the odds of getting 1 or 6 equal, remember the formula is the probability of A or B is the probability of A, event A, plus the probability of B or event B, minus the probability of event A and B happening, right?
Yes.
But now, we know that on a die, 1 and 6, 2 and 4, 3 and 5 just can never happen on a die. So that falls off, it becomes 0.
It's null.
It's null, yeah. It's null. So then that gives us that. And we can also use this rule for the number of elements or outcomes in each event if the events are mutually exclusive. So this means, if you think about it from in each event, so number of elements A or B equals number of elements of A plus number of elements of B. Alright? And when two events are mutually exclusive, they don't overlap. So the intersection of A and B is empty, and we write that A intersecting with B is empty, right? So the intersection of A and B is empty. This goes back to the thing I was talking about, symbols. There are quite a number of symbols. Here's another symbol.
What does that frowny smile mean?
That's intersection.
Oh, when it's smiling, it's not intersection.
This one is frowning, it's intersection. This just means empty. And this is empty set. and this is intersection. Then the probability of A intersecting with B. Wait. What's this sign again? And let's quickly look them up. Intersection symbol in math. Yeah. Okay, intersection, yes, is the one that's frowning. And then let's look at union. I want to just see union symbol in math. Yeah, so this one would mean union. So the probability of the union of A and B is 0.
I see. This.
And then there's subset, not
subset.
subset. Yeah. So
You're there, boy.
you see, so I'm not privy to all the symbols,
I can see.
but there are a lot of symbols. Okay, so I'm also very tired.
And you can view it.
Yeah, no, I'm very tired right now. I've had a long day.
Yeah.
So we're gonna stop here, but let's carry on this conversation on our Friday class, where we will continue from complementary events, still probability. Because I think if we do and cover as much ground as possible on this topic of probability, and we also document it online, that would be great. And it will also help us to have reference material for your digital tools study support, so you can always access the content.
Speaking about that, there might be a probability. You see the irony in there?
Probability.
So what I did there?
Yeah.
There might be a probability of me tomorrow not being available because...
No, we're having our next class for maths on Friday.
I mean on physics.
It's on physics. Oh, tomorrow's physics, yes.
Dear Lord, you forgot it's physics.
I thought you were talking about the math, but
Oh
okay.
no, I'm well aware that mathematics is on Friday.
Yeah, okay.
You made a great statement when I was confused and arrived here on Tuesday. Because, Tim, what are you doing on Tuesday? the first thing you said was, Tim, what are you doing on Tuesday? And I said, I'm here for class. And you said, no. Website is PC. No.